The next definition, the next terminology comes is the definition of continuous function in two variables. So let us start with the definition. So a function f of two variables, basically a real valued function, of two variables is called continuous at a point a comma b if it satisfies the following conditions. So condition, we know that the value of the limit, first of all, it should exist, and the function is, for the continuity, the value of the limit should be exactly the value of the function at that point, right? So basically we are extending the definition of continuous function at a point to continuous function for two variables. So the function is said to be continuous at all points a comma b in R2 if the function is so this if the function is continuous at each point a comma b, right? So basically that satisfies this definition. For every point a comma b, then the function is continuous everywhere. So let us start with an example. So more or less this example we discussed in the last lecture at the end. So show that the function xy, which is defined as x square plus y square times sine 1 divided by x square plus y square, if the point x comma y is not equals to 0 comma 0, and the value of the function is 0 if our point xy is origin. So we want to show that this function is continuous at the point 0 comma 0. So to check that this function is continuous at origin, by the definition of continuous function, we need to take a comma b equals to 0, and we need to substitute the value of the function. So essentially what we want to prove here is we want to prove that limit xy approaches to origin, value of the function, that is x square plus y square sine 1 divided by x square plus y square. We want to show this limit exists, that is the first condition, and the value of the limit should be f00. So f, the value of the function at origin, is given to be 0. So that is what we need to check, that this limit equals to 0. So this is our claim. So to show that this limit what we'll do is here, first thing we need to show is the limit exists, and limit exists we usually show by either the sequence approach, or we can use the epsilon delta definition. So here we use epsilon delta method to show that the limit exists. So therefore we need to prove that so let us recall the epsilon delta definition, that is for the two variable function. So that is for every epsilon greater than 0 there exists a positive number delta greater than 0, such that whenever we have 0 less than square root of x minus a square plus y minus b square less than delta. So a comma b is 0 0 here implies f of xy minus l is less than epsilon. So limit we want to show it is 0. So therefore L we will take to be 0. So we need to show f of xy sine 1 upon x square plus y square minus the value of limit should be less than epsilon. Right. So this is our claim. Essentially, we want to show that the limit exists and it is 0. So let us see if we can prove this. If we can show that this for every epsilon we can find such a delta which satisfies this property, then we'll be able to say that the limit exists and value of the limit is equals to 0. Right. So what we will do last lecture, if you remember, we will squeeze this function, this value modulus of this by square root x square plus y square in terms of that. So let us start with that. So note that modulus of x square plus y square times sine 1 upon x square plus y square. This modulus, as we know that the sine function takes value between minus 1 and 1. So therefore modulus of sine will be less than or equal to 1. So therefore we will get modulus of x square plus y square times sine 1 divided by x square plus y square, and now we can use this is less than or equal to x square plus y square, because modulus of sine x square plus y square is less than or equal to 1. Right. So essentially what we are discussing here is that we are checking the given function is continuous at point a comma b. So to check the continuous function is the function is continuous at a comma b, we need to check this particular limit, right, as in the one variable case. So at origin for this particular function, basically to check continuity at origin we need to check this condition. So limit exists and it equals to 0. So now to check this limit, essentially we are showing that the epsilon delta definition is satisfied. So basically we want to prove this criteria to show that this limit exists. And therefore we started with as in the last lecture, that we start with modulus of this function which we want to show it is less than epsilon. So modulus is less than equal to x square plus y square, that we have already observed here, using that modulus of sine function is less than equal to 1. So now what we need to check is we need to convert x square plus y square in terms of delta, right? So we know that square root of x square plus y square is less than delta. So if we square this inequality, then we will get x square plus y square is less than delta square, right? So essentially what we'll get is we will get x square plus y square less than delta square. But what we want is we want this quantity to be less than epsilon, and this quantity we got less than delta square. So that will give us a hint that therefore we choose epsilon equal to delta square. So delta we will choose such that epsilon equals to delta square, and that will give us delta to be square root of epsilon, because delta and epsilon are positive numbers, right? So delta, if we take square root less, if we take delta to be square root epsilon, then this condition will be satisfied using this computation, right? So this delta will satisfy the statement star. So what is the statement star? Statement star is basically this statement. That is what we are checking using limit exists using epsilon delta method. So therefore what we have proved is we proved that limit of xy approaches to origin x square plus y square sine 1 divided by x square plus y square equals to 0. Right. So this is just an example which we have taken, that the function, therefore the given function is continuous at origin. So this is just to give you an idea that how we can show, if we have such an example that given function we need to check at a given point, we can use this approach of epsilon delta method to show that the limit actually exists and it equals to value of the function at that point, and therefore the function itself is continuous there. So just I wanted to discuss one such example. The next method is we will check the limit using polar coordinates. So in for two variable function, we discuss so far two methods which are used essentially, which we shall use essentially, that is sequential approach as well as epsilon delta approach. But for two variable function, we have a third way to find the limit, that is the polar coordinates. So we know that the polar coordinates are, if we have a point xy in R2 plane, then we have a radius defined and angle defined. So how we can define, so the point should be non-zero, right? XY point should be other than origin. So how do we define R? So first of all, in polar coordinate, x is R cosine theta, y is R sine theta, right? So therefore what we get is we get x square plus y square is equal to r square, and that will give us r is equals to square root x square plus y square. And similarly we can compute theta, which is tan inverse y divided by x. So from these polar coordinates, how will we relate the xy approaches to 0 0 with polar coordinates? So xy approaches to 0 0, that means what? That means x and y basically both are approaching to 0, and that will give us square root x square plus y square approaches to 0. Right? So whenever our point xy will go close and close to 0 0, the term square root x square plus y square also goes to 0. And this is what is this square root x square plus y square is nothing but r. So r radius also approach to 0, right? And converge is also true. R is equals to x square plus y square, square root x square plus y square. And if square root x square plus y square approach to 0, then one of the remark we have seen that says that the point x comma y approaches to origin. So whenever we are given a function, what we will do, we will replace the limit xy approaches to 0 0 by the limit r approaches to 0, and we will convert the function in polar coordinates using this formula. So let us see if we can see some example here in terms of limit in the polar coordinates. So using polar coordinates, show that limit xy approaches to origin x square plus y square cosine 1 divided by x square plus y square is equals to 0. So we want to show this limit. So the limit is essentially nothing but the last example, just we have replaced sine function by cosine function. So let us see if we can show that using substitution of the polar coordinates. The first thing what we do is substitute x equal to r cosine theta, y equal to r sine theta, and use the implication that xy approaches to 0 0 if and only if r approaches to 0, right? So what we get is so our function given to be limit xy approaches to 0 0, x square plus y square cosine 1 divided by x square plus y square, right? So this limit we want to show that it equals to 0, but not directly using xy coordinate, but we'll first convert it into polar coordinates, and then we'll take the limit will convert to limit r tends to 0. So let us substitute all these things. So limit xy approaches to 0 0 will become limit r approaches to 0 using this, and our function, if we substitute x equal to r cos theta, y equal to r sin theta, then we know that x square plus y square will become r square, right? And the function cosine will become 1 divided by r square. Cosine is as it is. Cosine function will be as it is. So now if we observe, we can see that now the function has become only one variable function in terms of the r. Right, so this is the limit of a function of one variable. So function is converted into only one variable r, and we have limit r approaches to 0. So such a limit we have already studied in the in calculus, this M1 course, that how to find the limit. We have a function of only one variable x. So here instead of x we have variable r. So how we will show that this limit equals to 0. So can anyone suggest?
Frequency of cos use कर सकते हैं सर.
सर एक्सपेंशन कर सकते हैं सर cos का.
Okay, any other way? So can we apply squeeze theorem or something? So this type of examples we have studied in the
squeeze लगा सकते हैं ना सर उसमें.
Squeeze we can use, right? So what essentially we will use is again we will use that the range of cosine function is between -1 and 1. So modulus of r square cosine r square 1 upon r square is less than or equal to r square. All right, so you can use the squeeze theorem. So note that modulus of r square cosine 1 upon r square is less than or equal to r square, and this is modulus, so always non-negative. So as r approaches to 0, r square approaches to 0. This is anyway 0. So therefore by squeeze theorem, this limit also will be 0. Right? So note that 0 less than or equal to mod r square cosine 1 upon r square less than or equal to r square. And therefore by squeeze theorem or sandwich theorem, we get limit r approaches to 0, r square cosine 1 upon r square equals to 0. So we proved that this last limit equals to 0, but that is nothing but this limit, right? We just converted into polar coordinates. So therefore the original limit also equals to 0, right? So therefore if you want, I can write down the final answer that so therefore limit xy approaches to 0 0, x square plus y square cosine 1 divided by x square plus y square is 0. So this is an example of showing limit using polar coordinates. Now the question is, in this example the limit actually exists, so we have used the polar coordinates. But what if the limit is path dependent or something? How it will reflect in the polar coordinates? So let us see one such example where the limit does not exist. So find limit xy approaches to 0 0 of the function x square divided by x square plus y square if exists using polar coordinates. So here the question is that first we need to check whether limit exists or not using the polar coordinates. So let us start with so our first step is to substitute x equals to r cos theta, y equals to r sin theta, and we'll take limit r tends to 0. So our function will becomes function of one variable, right? And we know how to find limit in one variable case. So let us first convert do this procedure. So note that our function is limit xy approaches to 0 0 x square divided by x square plus y square. So if you substitute x equal to r cos theta, y equal to r sin theta, so what we'll get is this limit equals limit r approaches to 0 instead of limit xy equals to 0, and x square will become x is r cos theta, so it will be r square cos square theta divided by x square plus y square. So we know that if x is r cos theta, y is r sin theta, x square plus y square is r square. Right, so now we can cancel r square. So essentially we'll get limit r approaches to 0 cos square theta, because r square we can cancel, r is a positive number, we can cancel that. So finally now we have limit r approaches to 0 cos square theta. Now theta does not depend on r. So theta is cos square theta depends only on theta, it does not depend on r. So therefore limit of this will be cos square theta. So it is like limit of a constant. Cos square theta only depends on theta, it doesn't depend on r. So what we get is we got value of this limit L to be cos square theta, right? So now what we need to check is this limit L should be unique, it should not be different, right? The value of L should be same if we approach xy to origin. But what we got is actually is L we got is cos square theta, right? So here the limit in polar coordinates is cos square theta, which depends on theta. So for example, if we take theta equals to 0, if theta equals to 0, then L is equals to cos square theta is equals to cos square 0. Cos 0 is 1, so limit is 1. So what is this? So if we see in the diagram, so theta is equals to 0 means our point is on the x-axis, right? X comma y, where y is 0, because our angle is 0 here. So we are approaching a row, our point xy approaching to 0 0 along xy, along the x-axis. If we take theta equals to let us say pi by 2, theta equals to pi by 2, then what is the value of L? Value of L is cos square pi by 2, and then we know that cos 0 is 1, cos pi by 2 is 0. So value of limit is 0. So now the angle is pi by 2. So where should be our point xy? Our point makes pi by 2 angle with the x-axis. So that means our point is here, right? Point xy is on the y-axis. So therefore its first coordinate will be 0. Right? So what this says is, if we approach xy, our point xy approaches to origin along x-axis, then the value of limit is 1. If our point xy approaches to origin along the y-axis, then theta is pi by 2 and the value of limit is 0. So therefore what we are saying is that here the limit in polar coordinate is cos square theta, which depends on the value of theta. So therefore it is not unique. So it does not exist. So this is what we are getting for this example, that the limit does not exist. So why it does not exist? Because when we convert the limit into polar coordinates, we are getting value of the limit is cos square theta. That depends on theta. But if you see in the previous example, when we convert into polar coordinates, there was no theta term. Only the limit was in terms of r. So therefore we were able to use the limit squeeze theorem for the function of r. So the second example we can also do by our usual limit approach, and we can substitute y equals to mx, and we can see that the limit is path dependent. But what we wanted to see here is using the polar coordinates. So now the next thing which we want to discuss is so we discuss iterated limits. So that is a kind of special a particular way to find a given limit by applying limit at a one time in a particular variable. So there is a similar notion of derivative for the function of two variables, that is called partial derivatives. So there we take the slope in either variable, either in x variable or in the y variable. So before we discuss the partial derivative, I need a definition of interior point. So we know that for one variable function, when we check the differentiability of a function, the interval should be open interval, right? Usually in the mean value theorem. So that is because at the point where we are discussing the differentiability, we need slope at that in the neighborhood of that point, in the delta neighborhood. So the same way here also we need at the point we need differentiability, we need enough points close to that point in the domain. So that idea is basically the interior point. So let us just see what is the definition of interior point. So if we have a set which is subset of R2, a point A comma B in this set is called an interior point if we have a So we consider a circle x minus a square, y minus b square less than r square. This set, which is interior of this circle, should be subset of domain, right? For some r greater than 0. So let us see what this geometrically means. So if we draw the diagram, so our set D is a subset of R2. We say that a point A comma B is interior point if we can find a small enough circle around that, right? So here the radius is R. So if this all the points inside this circle they belongs to D, then we say that the point AB is interior point of the set D. So let me repeat the definition once again. So given subset of xy plane, a point inside that set D is called interior point if around that point we can draw a small circle whose inside points belongs to D. Right. So this is saying that in one variable what we say is the delta neighborhood x minus delta to x plus delta is a subset of domain for the differentiability. Instead of that, now here we have a interior of the circle which is inside domain. So let us see the definition of partial derivative. So let our domain is a subset of R2 where f is a function from T to R. So D is a subset of R2 which is the domain of the function. So let A comma B be an interior point of the domain D. So we say that the partial derivative of the function f with respect to x at the point A comma B exists if so let me write the condition on the next page. So if the limit so we know the slope, how we find the derivative in one variable. So the same definition we'll use here, that f of a plus h comma b minus f of a comma b divided by h exists. So in one variable we know the value of the limit is limit h tends to 0 f of a plus h minus fa divided by h. That definition we are extending for the first variable here, so therefore it is called the partial derivative of the function in variable x, the first variable. So notation what we will use is, so there are two notations.
सर एक बार स्क्रॉल अप करेंगे प्लीज.
So that is a previous slide basically. So we are saying that the function f has a partial derivative with respect to x at point a comma b if this limit exists. So limit is what? Limit is, so let me write that again. So what notation we will use is del f by del x derivative at the point ab, partial derivative at the point ab is limit h approaches to 0 f of a plus h comma b minus f of a comma b divided by h. So what does this represent? This represent we are changing the function in the first variable, in the x variable. So this is first notation. Second notation we'll use is the fx at a comma b. So this thing del f by del x we will shortly write by fx, f subscript x at the point a comma b. That also means limit h tends to 0 f of a plus hb minus f of ab divided by h. So the condition is that the limit should exist. If the limit does not exist, we say that the function is not partially differentiable with respect to x at the point a comma b. So if this limit exists, then we say that f is partially differentiable at x, partially differentiable with respect to x at the point a comma b. And if the limit does not exist, we said that it is not partially differentiable with respect to x at the given point. So similarly, this is a notation for fx. Similarly, we will use the notation for the second variable. So similarly, we can define the partial derivative with respect to the other variable, and we'll use the notation fy at ab equals to limit k approaches to 0. So now h we have used for the derivative with respect to x. So for derivative with respect to y, we will use k. We may use h also, but usually in books you will find that for the other variable we essentially use k. So what we are changing is we are changing the second variable now. So we are taking slope in the second variable, and then we are taking limit of the slope. So that is the derivative. If the limit exists, and for the same we also use the other notation, that is del f by del y at the given point a comma b. So this will give us two limits, limit in the first coordinate and limit in the second coordinate, fx and fy at the point a comma b. So combining these both limit in both the coordinate, what we get is known as the gradient. So today I think we will not be able to cover the example that we will take in the next lecture. But let me state this definition at least. So the gradient of the function f at the point a comma b is the point del f by del x a comma b partial derivative with respect to y evaluated at a comma b, and the gradient is denoted by, so notation for gradient is del f a comma b, right? So what we will use is, we will use the notation the gradient of f, gradient of the function f at the point a comma b is nothing but partial derivative with respect to x at a comma b and partial derivative with respect to y at that particular point. So if fx and fy we cannot find at a particular point, that means limit does not exist, then we cannot find gradient also at that point. So gradient we can find only when the limit exists, both the partial derivative exist. Otherwise we cannot find the gradient. So I think this is